Hello folks, this is the first lecture on special relativity, and I'm going to teach you the entire theory of special relativity in just a few short minutes. As it turns out, there's only two principles in special relativity: the principle of relativity and the light postulate. If you know those two things, everything else is just a detail. The principle of relativity says that the laws of physics are the same in every inertial frame of reference. How can there be two different inertial frames of reference? Well, one could be on a train. I've set up a bunch of rulers and clocks on my train, and I say these rulers seem to be at rest on my train. This allows me to look out the window and say, those trees are passing me by. The trees are in motion with respect to the train. They're in motion with respect to my train's reference frame. Similarly, someone on the side of the tracks will have a reference frame set up at rest with respect to the tracks, and they'll say about me on the train that I'm the one that's moving. Now, the principle of relativity says that as long as we're each moving with constant speed in a straight line, we will have the same laws of physics. You might have heard of this one. It's called Newton's first law. Every body continues in its state of rest or in uniform motion in a right or straight line unless it is compelled to change that state by forces impressed upon it. Bodies in motion will stay in motion, bodies at rest will stay at rest unless acted upon by an outside force. Newton's first law is true in every inertial reference frame. Let me try and give you an intuition for what that means. You held a cup of coffee in your classroom before, and you were at rest. And the coffee, it just sat there in the cup until you decided to have a drink. But compare that to holding a coffee in your car when your friend driving decides to slam on the brakes. What happens? Your coffee spills all over you. I just bought these pants. I can't believe it. The difference between those two motions is that one was inertial and the other one was accelerated. When motion's inertial, you almost can't tell that you're moving at all. It's sort of like being on a plane. When you wake up, you start to hug your pillow only to realize you're not home at all, and that your pillow is the person's arm next to you. I'm very sorry about that, sir. Am I the only one that this happens to? Now, as long as the plane is moving in a straight line at constant speed, it is very much like your bedroom. Coffee doesn't spill on you. It feels like you're at rest. Newton's law is really different from what they used to believe in, for example, ancient Greece, that if something was in motion, it would slow down until it got to its natural state of rest. True absolute rest. That law is saying a body in motion will change. It will come to a rest. A body at rest will stay the same. These are two different reference frames and two different laws. That means it's incompatible with the principle of relativity. The principle of relativity is sort of like a meta law. It's telling you about how the laws of physics must be, and it says in particular, whatever they are, they must be the same in every inertial frame of reference. Now, there are a couple of interesting implications of this principle alone. One of them is absolute motion cannot occur. If the principle of relativity is true, which reference frame would it apply to? This one or that? Well, the laws of physics have to be the same in every reference frame, so we can't identify one as being absolute motion. Another consequence is this: the laws of physics tell us what kinds of experiments are possible. If the laws of physics are the same in every reference frame, that means that experiments will run in the same way in every reference frame. Galileo put it in this charming way. He said, imagine you had a laboratory on a boat, and that the boat was moving with very constant speed in a very straight line. I have all kinds of experiments I can set up. I've got an inclined plane. I've got a large hadron collider experiment compressed into a small space. I've got some butterflies flying out of a bottle. No butterflies were heard in the making of this video. Oh, I love butterflies. Whatever experiments you like, I set them on a boat, and I compare them to the very same experiments set up on Earth. If the motion is truly inertial, the results of all those experiments will be the same. If the ball rolls down the inclined plane on the boat, it will do so on Earth as well. So because the laws of physics are the same in all inertial reference frames, so too must be all experiments. And if all experiments are the same in every reference frame, then there is no experiment you could ever do which determines which state of motion is absolute rest. Now you might say, look, I feel like I'm at rest. Absolutely, I'm at rest. I'm sitting on my couch watching this video. What more rest do you want? Oh, but come on now, you're not so at rest, are you? You're actually on a spinning orb. And that spinning orb is spinning around another orb, spinning around the center of the galaxy, and the galaxy is hurtling through space, and you're not at rest at all. You're actually in this incredibly complicated motion. A consequence of the principle of relativity is that no experiment can tell what absolute state of motion is. So in summary, the principle of relativity says the laws of physics are the same in all inertial frames of reference, and this implies that absolute motion can't appear in any law of physics, that all experiments run the same, no matter which inertial reference frame you're in, on the boat or on Earth, and that no experiment can possibly reveal the absolute motion of any observer. It's almost as if absolute motion doesn't exist. You learned the first principle of special relativity. Are you ready for the second? The second principle is called the Light Postulate, and it says the speed of light in a vacuum is the same in every inertial frame of reference. What is the speed of light anyway? It turns out it's fast, really fast. 186,000 miles per second fast. This means that if you were to measure the speed of light on a train, no matter where it came from, you'd find it's going 186,000 miles per second. If you were to measure it off the train, also 186,000 miles per second. And now this is weird. This is really different. It's not like almost anything that you're familiar with. Here's an example. Let me go back to the motorway. If it weren't another car, but it were a beam of light going 186,000, and suppose I were going 185,000, a person on the side of the road would say, wow, that's two really fast things going by. A light beam is traveling at 186,000 miles per second. And you, in this incredible spaceship, I know my spaceship is incredible, and according to the light postulate, although I'm traveling at just a hair less than the speed of light, I will still look at that same light beam and say that it's going 186,000 miles per second. That's strange. Most things are not like that. So if the light postulate is so weird, why do we believe it? Einstein didn't get these principles out of nowhere. He was looking at the most advanced theory of the time that was the theory of electricity and magnetism, or electromagnetism. The theory of electromagnetism just worked if you made this assumption. You got all the right predictions about current flowing along wires, about the way that magnets work, about the way that magnets work when they're near electric wires. And after trying lots of different theories, this one with the light postulate turned out to be what worked. Einstein tried other things, but they didn't work. And this, it turns out, is the core of special relativity. The principle of relativity, that the laws of physics are the same in all inertial reference frames, and the light postulate, that the speed of light is the same no matter which inertial reference frame you're in. In the next lecture, we're going to see some of the really surprising things that these two principles imply. Thanks so much for coming, folks. I look forward to seeing you next time.